So, good morning everyone. So, this is really the last class and you won't have any more torture from me, isn't it? Okay, so in the last class we had just started the discretization of the weak form. Okay. So, we defined our increments delta r as delta r little I ni, similarly for delta theta, which was delta theta I ni, and same way for del r and del theta. Okay. So, you see these are discrete approximations of these four functions. So, what we have to do is we just plug in the discrete approximations in the weak form and then it just becomes the discretized weak form. So, for example, our G static that we had defined. So, when we plug in the discrete approximation, it becomes discrete. So, we use a superscript h to define that it is discrete. Okay. So, this becomes, let me just write down the actual G, which was n m dot E transpose del r del theta minus the term due to distributed load and the boundary condition. Okay, and these NP and MP are the prescribed forces and moments at the ends. So, this is the weak form without being discretized. So, I should not put this H here. Now, we have to plug in these approximations over here, isn't it? And you see we have this operator E. So, we have to also discretize that operator. So, that E transpose was defined as the identity d over ds, then here we had this little r prime and it is skew symmetric, then the 0 tensor and identity d over ds. So, we have to discretize this. So, you can note this, for example, when it acts on this del r del theta vector, then this becomes del little r prime plus r prime cross del theta and del theta prime. Okay. So, the whole idea was to write this using this operator E transpose, isn't it? And now, when we discretize this, you see what is going to happen. Let us just plug in del r prime, which is discrete approximation. So, here we say it is approximate, and del little r prime then becomes del little r I n I prime. See, the prime shifts onto the shape functions, because the del little r I, they are constants, right? They are not functions of S. All S dependence has now shifted onto the shape functions. Okay? So, we take the prime onto the shape functions plus little r prime. So, little r prime remains as it is, okay? Because we have discretized just the increments and the variations cross del theta. So, that also becomes cross n I del theta I, and then this del theta prime then becomes del theta I n I prime. Okay? And then we can write this again using the discrete operator. You will see how to get that discrete operator E transpose. So, if I write this as n I prime identity, then n I little r prime cross 0 n I prime identity times del little r I and del theta I. Okay. So, you see you have now gotten your discrete operator, the discrete form of that E transpose. So, this is simply, you can define it as E transpose with a subscript I. Okay. You could also put in some h to say that it is a discrete form, but let us not burden it with so many symbols. If you have the subscript I, because you see in this matrix you also have these ni's. So, therefore, this comes with a subscript I, okay? And then this gets multiplied with del little r I del theta I, isn't it? All right. So, we are going to use that, of course. So, then our G S T H, the discrete H is then 0 to L N M dot E I transpose, where E I transpose is that number over there, that matrix, del little r I del theta I. Okay. And you see, what about these one, these N and M? They are simply your integrands which have to be evaluated. This is also getting integrated, right? ds. So, you have to integrate this from 0 to L. So, you would have the current state, right? What is little r and little theta. So, corresponding to that current state, you find out what is the current strain V and K, and then from constitutive law you get your N and M. Okay. So, these depend on the current state little r little theta. Remember, this was a function of little r little theta and this del r del theta. So, little r little theta, we are defining your current state. So, find out the strains from using this current state and get your n and m, and then you integrate. Okay. So, that is just the first term. Then we talk about the second term, minus 0 to L, and the second term is quite easy. N hat and m hat are the distributed load and distributed couple. So, usually they are prescribed. So, depends on how you have prescribed it. You can put that function here, and then you dot this with the approximation. So, del r you put it as ni del r I. So, ni would just come out, and this becomes ni del r I del theta I, isn't it? And then the last term, can you guess what happens to the last term? See, we have to evaluate that at the boundary. So, what is del little r of L? So, let us just do that side calculation. Del little r of L, that is simply ni at L times del little r I. But what is ni of L? You remember your shape functions, if this is your rod and you have going it from 0 to L, and you discretize this as we have done last time with nodes 0, 1, 2, n minus 1, and the last node is n. That is how we have discretized this. So, what is big Ni of L? You remember the property of the shape functions, we have to evaluate those shape functions at L, for example. So, what will be big Ni of L? The shape functions were such that the ith shape function was 1 at the ith node and 0 at every other node. So, when you evaluate the shape functions at L, which is the nth node, right. So, only the shape function corresponding to, let us make it little n, so that does not confuse with our shape function over here. So, only the shape function corresponding to the last node will survive there, all others are gone, right, and that is also equal to 1. So, this is simply equal to n, the nth shape function evaluated at L times del little r n, and this is nothing but 1. So, this simply becomes del little r n, right. So, what does that become then? So, you will have n p at L, the force that you have prescribed at the Lth node at S equal to L, m p at L dotted with del little r n subscript n, del theta subscript n. So, that is just one of the boundary. Then you also go to the other boundary and you write it as with a plus sign, then, right, with a plus sign. N p at 0, m p at 0, and dot with del little r 0, del little theta 0, isn't it? Where these are the prescribed forces and moments at s equal to L and s equal to 0. In case of cantilever, for example, when you have a cantilever which is clamped at one end and you are applying a force at the other end, let us say P E1, then NP of L is simply PE1. So, NP of L is simply PE1. So, that is what you are going to put here, and MP of L is 0. You are not prescribing any moment. What about NP at 0? NP at 0, it is not known to you. You will get it by solving the equilibrium equation. But del little r of 0, the variation at s equal to 0, that is going to vanish, because the variations have to satisfy the kinematic boundary condition, isn't it? So, del little r at 0 is 0 and del theta 0 is also 0. So, that is how you take care of this 0 boundary condition. So, this actually vanishes. So, this vanishes in cantilever problem, not always, but in case of cantilever. Okay. All right. So, that is your discretized weak form. Now, I will like to write it as some global vector, we call it a global vector big R for residual, dotted with the vector of the variations at each of the nodes. So, for example, here you have del little r 0, del theta 0, del little r 1, del theta 1, keep on going to the last node, del little r n, del theta n. Okay. So, that is the vector of the variations at the nodes, and we will just call it your del vector, okay, without any superscript subscript. Then this is that whole global vector of del, big R dot del. Now, if that is the case, can you now think of what should be this big R? Given this your G, so this G static H, so we want to write it like this, some vector which we call it as residual vector dotted with the vector del. So, this thing we want to write it like this. Then can you think what should be this big R? How will the components of big R be defined? You can again think that this big R will be formed of sub vectors, small vectors, just as over here. See, this is a 6 by 1 vector, that is a 6 by 1 vector, and there are n plus 1 of them. So, that is actually 6 times n plus 1. So, this also would be a vector of dimension 6 times n plus 1. So, what will be the individual components of this vector? You can think that this is also formed by your big R 0, big R 1, keep on going till the last one, big R n, and this we just call it as the big R vector without the subscript. So, if that is the case, what do you think is the sub vector big R subscript I? So, this is the global vector and the small vectors we call it sub vectors, sub vectors. Okay. So, what is big R of I? So, big R of I, as you will see, is then dotted with del r I del theta I, is not it? So, then it means you just have to get the components or the coefficient of del r I del theta I, that will be your big R I, is not it? So, you come over here, extract the coefficient of del little r I del theta I, that is going to go in del big R I. So, big R I is then 0 to L and you see this is a matrix without any differential operator. Look over there, this does not have any d by ds. So, this is a usual matrix, it is not an operator now. So, now you can bring it on the other side, right, and the transpose is gone. You know, if this were not discretized, if this were without that sub I, just as you see over here, you cannot bring it on the other side, because this is with that d by ds which has to act on del little r. So, you can't bring it on the other side, but once it is discretized, there is no d by ds, it is a usual matrix, it is no more an operator, you just bring it on the other side in the usual way. So, when you bring it on the other side, that transpose is gone and it is simply E I times N m, which is dotted with del little r I del theta I. So, you can very well see what is the coefficient of del little r I del theta I. That is simply E I N m, right, ds. So, of course, that is just one component of big R I, then you also have to take it from here. So, that is also not hard, 0 to L N I N hat M hat ds, right. And the last one that you see over here, this will not go for every I, it only goes either over here or at n, because it has the coefficients del r n, del theta n, del little r 0, del theta 0. So, this one only goes over here or here, not in between. So, I will just write that the boundary term only goes to sub vector big R 0 or big R little n. So, of course, big R 0 has these terms also, but it will also have contribution from boundary term. So, that is how you can form your residual vector big R, all right. But still it is not really done. When you form your big R I, what you see is that you have to integrate from 0 to L, is not it? It is not easy yet. So, for each of these sub vectors, you work out the integration from 0 to L. So, here you know what usually called assembly of the vectors, assembly of residual vectors. That is something you can exploit. So, we will talk about how to assemble that residual vector. Now, if I look at those big R I, it is an integration from 0 to L. Why do not I divide that integration in terms of elements? You see, your rod has been divided into n elements, small n elements. There are n plus 1 nodes, so it is divided into n elements. Why do not I divide this integration into n elements? So, this becomes summation over E equals 1 to n. So, that is the summation over the elements S E minus 1 to S E. When E is equal to 1, it goes from S 0 to S 1. When E is equal to 2, it goes from S 1 to S 2, right. So, this is being done over the element E. So, that is the domain of element E, and then within it you have big E I n m d s minus 0 to L big N I n hat m hat. And yes,
I think that should also expand all the element. Huh?
which one?
The last.
Oh yes, sorry, yes, of course. So, this is I will just put a big bracket here. S E minus 1 to S E, and now you can exploit the property of the shape function. When I am doing the integration over the element E, not all the shape functions are active there, isn't it? What shape functions are active there when you are over the element E? 0, 1, E minus 1, E to little n. So, that is your element E. So, either this shape function or this shape function. So, that is the shape function n E, that is n E minus 1. Only these two are active on this domain, others are all 0. So, what you could do, for example, you can run a loop through the elements. So, you can have a outer loop which is running over the elements, and then within that loop you only evaluate the big R i's for those i's which are active there, right. So, for example, when you have a loop running for E equals 1 to n and you come inside, then you only evaluate big R E minus 1 and big R E. So, you only evaluate these two, because the contribution due to this element for other subvectors are 0. So, that is how you can assemble. So, you go through the loop, find out the contribution for R E minus 1 using this formula. So, R E minus 1, for example, is maybe I can just write here. So, Re minus 1 plus equal to summation S e minus 2 to S e minus 1 E I minus, so E e minus 1 N m ds minus summation S e minus 2 to S e minus 1 N e minus 1 n hat m hat ds. And you see I am saying here plus equal to, because your Re minus 1 would have been computed in some other element also. So, whatever has been built up till now, you just add this to it. So, that is called assembly. One by one you are start assembling it and adding here. Similarly, you write it for Re plus equal to. So, over here it is simply the integration would run S e minus 1 to S e, and this would be E subscript E n m ds minus S e minus 1 to S e n e n hat m hat ds. Okay. So, that is how you assemble your residual vector, and of course, once you are done through this loop, then you also add the residual vector corresponding to the boundary term R 0 and R n. Okay. So, that is how you can assemble your residual vector. There is of course one more thing remaining, how to work out this integration even within the element. So, how to work out integration within the element. So, for that you can use some numerical integration technique. You can use some quadrature rule, and instead of this continuous integration you can form a discrete integration, right. So, you have to work out numerical integration. So, I will skip that part, that is present in many of the FEM books, you can look there. All right. So, this is how you assemble your residual vector, but then you also have to look at your stiffness matrix. You had the linearized weak form also, and you have to discretize that. So, let me just write down the linearized weak form, which we wrote as dg, d for linearized form. So, that was an integration from 0 to L of pi h pi transpose, which we had defined last time, times E transpose del little r del theta dot with E transpose del little r del theta. So, this is delta, this is del, plus 0 minus n cross 0 minus m cross delta little r delta theta dot with E transpose del little r del theta plus n cross delta r dot del theta plus the contribution from distributed load and boundary terms. Okay. So, this is something that we had written down last time and plus this. Now, think about the cantilever case. In case of cantilever, the weak form had n hat m hat dot with del little r del little theta from the distributed load. So, when you linearize this term to find out what is its contribution in dg, what do you think? How will this term contribute over here in case of cantilever? So, in case of cantilever, this is not at all present. So, it just vanishes. Even if there are cases where you have the load acting, let us say, vertically downward of constant magnitude, the load is not changing its direction, then this little n hat, little m hat won't change as the cantilever changes its configuration. So, remember how do you get the linearized weak form? You find out n epsilon and then do d by d epsilon of n hat epsilon, right? And epsilon were the way to change your configuration. But as you change the configuration, your n hat epsilon so n hat epsilon would be same as n hat if it is independent of the configuration. So, if that is the case, then d by d epsilon of n hat epsilon would simply be 0. So, for the cases when the distributed loads are independent of the configuration of the rod, then their contribution to the linearized weak form will simply be 0, is not it? Similarly, when you talk about the boundary term, in case of cantilever, the force that is acting is Pe1. As you change the configuration, as you perturb the configuration by epsilon, does Pe1 change? Pe1 does not change. So, d by d epsilon of Pe1 is also 0. So, that does not contribute to this linearized form. But what if you have the follower load? If the force acting is P d1, P times d1. So, if n hat P at L is equal to P d1, where d1 is your director. So, this is same as P big R E1. And now, you see if you change the configuration by epsilon, big R changes to big R epsilon. So, then it is going to contribute to the linearized weak form. So, you have to be careful about that. Okay. All right. So, for now we will just forget about the distributed load and boundary term, but you have to understand that they are also important. So, now think of discretizing this dgh. So, what you got to do is simply write it as pi h pi transpose, and you see you write this as delta r I n I. Okay, this was made del little r I n I. Let's make this delta little r j and j. So use j here and I over there. Okay. So and now you can see the shape function will then just get derivative because of this E transpose, and this simply becomes E transpose j delta little r j delta theta j, isn't it? And you then dot this with E transpose I del little r I del theta I. Plus you come over here 0 to L 0 0 minus n cross minus m cross, and then you get nj delta little r j delta theta j dot E I transpose del little r I del theta I, isn't it? Plus the last one, and that's simply n I guess this was delta little r prime. Yeah, this was delta little prime. Sorry, I missed that prime here. So this becomes ni nj prime n cross delta little r j dot del little theta I. So that's a discretization. And you know what's the goal here is that I would like to write this as some matrix which I would call as stiffness matrix K multiplied with the vector of increments delta, which will have the sub vectors delta little r 0, delta theta 0, delta little r 1, delta theta 1, going up to the last one delta little r n, delta theta n. So this vector, which I will call as the delta vector, the vector of increments, dotted with your vector del, the vector of variations. So I want to write this in this form. So what do you think, what will this K look like? How will this K matrix look like? So then you can think of the blocks of 6 by 6 matrices over here, 6 by 6 matrices. And if I call this small submatrix as K I j, and then when you work this out, which is called the quadratic inner product, a matrix times vector with another vector, this is same as k I j times delta I dotted with, sorry, delta j and dotted with del I. Isn't it? This matrix multiplied with the delta vector, that's kij delta j, and then you dot with this del vector, so you dot with del I. But now the kij's, they are your 6 cross 6 submatrix. So our goal would be to get that kij. Okay. What's this delta j? This delta j is simply, maybe I will write this more explicitly, that's k I j times delta little r j delta little theta j dotted with del little r I and del little theta I. So our goal is to simply get that kij. Okay. So any idea how you can extract that kij from your dgh? It's all there for you to extract, isn't it? See, it's multiplied with your delta j, and here is your del I everywhere. From the first term, for example, you bring that EI transpose on the other side, and it becomes EI. So what's your kij then? Kij is then simply integration from 0 to L of pi h, okay, that EI is also there, EI, E subscript I pi h pi transpose E j transpose. See, this is symmetric matrix, by the way, times your delta j no? Oh yes, so of course I was writing that thing, but now it is without the delta or the del. So this is your contribution to kij plus the contribution from here, which is 0 to L nj ei times 0 0 minus n cross minus m cross ds, and then we come to the last term. What's the last term going to look like? Can you think of how the last term look like? Over there, see, it only has the coefficients delta little r j. It does not have delta little theta j. So it just means that the kij, which is your 6 by 6 matrix, only has a small 3 by 3 matrix inside it, non-zero. So you could write this as plus 0 to L ni nj prime times this matrix which has delta little r and del theta. So, delta little r del theta. So, I guess that is going to come here, your n zero 0 0. See, when you have this, you multiply with your triangle delta j and then dot with del I, you will get that. So, you see within this 6 by 6 matrix only this 3 by 3 is non-zero, because it does not have coefficients for delta little theta j and delta little r I.
What about the symmetry of the whole thing?
Exactly. So, that is
Symmetric?
so as you can see here, this term, this is symmetric, and this H, for example, is your elasticity tensor, right? Del 2 psi by del v 2, del 2 psi by del v del k, it has that. So, this term looks symmetric, right? And that is called the material stiffness part, material stiffness matrix, you can say. And this is your geometric stiffness matrix, contribution to geometric stiffness matrix. And as you see here, the geometric stiffness part is not symmetric. And usually when you find your Jacobian, it turns out to be symmetric, but in this case it is not symmetric. It is because of the the coordinates that we have. The angle theta is not commutative, but this whole matrix becomes symmetric if you plug it in the configuration little r little theta corresponding to static equilibrium. So, at equilibrium this matrix becomes symmetric, but at any other configuration this is not symmetric. Okay. So, as you see right now, this is non-symmetric, but it becomes symmetric at equilibrium. So, I will just write here it is non-symmetric and becomes symmetric at equilibrium. Okay. All right. So, once you have your k I j, then you can get this global vector k, isn't it? And here again you have to think of how to assemble this. So, you can divide this integration from 0 to L in terms of elements, and when you work out in terms of elements, then you will see that not all I and j will be there for a given element E. For a given element E, you will have I corresponding to E minus 1 and E, and j corresponding to E minus 1 and E, right. So, that is once you run your loop through the element, you can assemble your global stiffness matrix. Just as we are doing for the residual vector, you can also do it for your stiffness matrix. All right. So, once we have assembled our residual vector and stiffness matrix, then what should be done? Yes.
Could you explain the last one again? Why does it become symmetry at equilibrium?
I mean, there is a proof. You have to go through the proof, and I don't have any physical answer why it is becoming symmetric, but you can prove it. And the proof is there in the CMOS paper. You go to CMO 1986. CMO and Woodcock, 1986, and you can find the proof. Okay. And he actually proves the not the discretized part, but the linearized weak form. He proves that that becomes symmetric. That's even better. If you prove the linearized weak form is symmetric, then of course once you discretize it, the discretized weak form will also be symmetric. Discretized linearized form.
I think this is due to the parameterization. No? I mean, if
Yes.
you get your primary variable, maybe the capital R's,
Yes.
and you work with that as
Yeah, it's
not then.
but even then, because it's not commutative, capital R.
Yeah, but the second derivative of something should
Yes.
be symmetric. No?
Well, this is also the second derivative of something, little r and little theta. It's the second variation.
Yeah, but somewhere there's a point
Yeah.
where the symmetry is broken. No?
Right.
Because the delta or the del theta is not the delta or the del of a vector. You get it by having a del or a delta of the capital R and then extracting from there.
Yes,
something.
of course. Yes.
So
Yeah.
it has to do with this large rotations.
Yeah, and which would be present even if you work with big R, right? And of course, you'll have constraints also.
I think that there are parameterizations where you can make it symmetric, but then you have other problems.
Yeah.
If you work with the whole of the capital R, you have
Yes.
all the 9 variables.
Yes.
And then you have to put a constraint
Constraints
to make-
also. Yeah.
because it's only 3 independent
True.
variables. So whatever you do, it's a
Yeah.
mess.
It's a mess, of course. Okay, so now we go back to what we had. Do you remember your G at little r plus delta r, comma theta? Of course, you won't say here, maybe you can say exponential of delta theta times exponential of theta del little r del little theta. So you remember you were doing Taylor expansion for this G. So this was equal to approximately equal to G at little r comma little theta, or you just say exponential of theta. Del r del theta plus the linearized term dg, right, which is a function of your delta little r delta little theta, and then of the current state little r exponential of theta, then your del r del theta, and then you had the higher order term, but you forgot about that because you only wanted to work with the linearized weak form. And we also saw that the linearized form was linear in increments and also in the variations. And you also, when you okay, so we actually had to solve this nonlinear weak form, right? We had to set this equal to 0, but this was not easy. Therefore, we linearized it, and then we said, why don't we solve this problem? But solving this was also not easy because it's a function. Therefore, we discretized it, and once you discretize it, then what does this become? See, your G, what did this become? This became big R dot del. And your dg, what did this become? k triangle dot del, right? And we have to set this equal to 0. So, we are solving the linearized weak form now. So, in the discrete version, this is what it is, you want to solve this. Now, because this has to hold for any variation, then in the discrete world it is same as saying that this has to hold for any delta vector. Okay. So, then you write this as big R plus k triangle dot delta equal to 0 for all delta. Of course, then you add this admissible, which have to satisfy your kinematic boundary condition. So, this is same as, that means this is same as saying that you have to solve this matrix vector equation. Okay. So, from here you then obtain your increment vector delta equals minus k inverse big R. Once you get your increment, then you change your state, your little r, you change it to little r plus delta little r. See, this delta vector has got both delta little r and delta theta also. So, you just extract the delta little r from this delta vector and add it to r, then you get your new guess or new state. And similarly, your theta, now that does not change so nicely. So, you have to kind of extract the theta from this matrix, exponential of delta theta times exponential of theta. So, you have to extract the theta from here. So, I will just write here extract. So, that is how you update your configuration. Once you solve this for delta, so this delta will have your increments at each of the nodes. So, you update the value at each of the nodes for little r and also for little theta. The updation for little theta is not so easy, because whatever theta you have, you find its exponential to get your rotation matrix and pre-multiply with the incremental rotation to get the final rotation matrix. And once you have the final rotation matrix, then you extract the theta from that rotation matrix. That gives you the final theta. Okay. So, this is how you update the configuration. Update of configuration. Once you have updated your configuration, then you find your big R again by assembling process, find your residual vector again and check whether it is 0. If it is close to 0, or if it is close to some tolerance, then you stop your Newton-Raphson. If it is not, then again find your stiffness matrix, again get your increment delta, again update your configuration, again find your residual vector, check. If you see that the residual is close to 0, stop. If it is not, then keep on doing it. So, that is your Newton-Raphson process. Okay. Now, in this whole thing, there is one thing which is very tricky, which is that once you update your configuration, and then you go to compute your residual, for example, residual vector or the stiffness matrix, you see that it requires the value of n and m, right, forces and moments. To get the forces and moments, then you will have to find out what are the new strains, right, nu v and nu k corresponding to the nu little r and nu little theta. Now, getting nu v and k is again not so easy. So, this was just updating the configuration. Let me also tell you how to update the strains, because that is what you need to get your forces and moments. Okay, so update of strains. So, V, for example, V is, so V, I will write new vector V strain would be new rotation transpose little r nu prime, and you have to get them at the quadrature points, isn't it? Because when you integrate in the element and when you convert that into numerical integration, you evaluate the integrands at the quadrature points, right. So, you have to get your strains at the quadrature points. You have, through this updation, you have found out the values of little r and theta at the nodes. Now, you need to get them at the quadrature point. How do you get this at the quadrature point? So, of course, one way is, so you have to use what is the isoparametric concept. So, you say that within an element little r, you can say it simply small r I n I. So, within an element, just as you do it for your increments, you would also say it for your configurations, and same thing also goes for your little theta, is little theta I n I within an element. So, from here you can then extract your little r prime at the quadrature point and your big R also at the quadrature point, right, and then you would get your V. So, that is not so hard. How about your K? To get your new K, new curvature, that is axial of big R transpose big R prime at the quadrature point. Now, you can find out your big R at the quadrature point, because once you get your theta at the quadrature point, take the exponential, you will get your rotation at the quadrature point. How to get big R prime at the quadrature point? Now, you might wonder, why do not I say that big R is also same as big R I at the nodes times n I. See, you have done it for theta. Can you do that for big R? You can't do it, because big R is a orthogonal matrix. You can't really sum two rotations and get a new rotation. So, you can't do this. So, how do you get your big R prime then? So, that is a tricky thing, how to get your big R prime. So again, CMO has worked out the formula, an exact, a very accurate updation formula for curvature. So I'm just going to write that. So curvature, new curvature is simply equal to old curvature plus new rotation at the quadrature point transpose times a vector beta, where this beta is quite messy, that sine of the delta theta at the quadrature point. See, this delta theta is at the quadrature point. You got your delta vector, right, from Newton-Raphson, this delta. So you have this delta theta at each of the nodal points. Then you use this isoparametric concept or through interpolation to get your delta theta at the quadrature point. Okay? So delta theta certainly was written as delta theta equals delta theta I ni. This we had of course used, and we also extended this to configurations. Over here what you need is your delta theta at the quadrature point. So you use this to get your delta theta at the quadrature point, okay, divided by the norm of delta theta into delta theta prime. How do you get your delta theta prime at the quadrature? Again, use this formula, plus 1 minus sine of delta theta divided by delta theta into delta theta dot delta theta prime over magnitude of delta theta times delta theta over delta theta prime, over magnitude delta theta plus half times sine of half of magnitude of delta theta divided by half of magnitude of delta theta. Quite messy, isn't it? Then you take its square and then delta theta cross delta theta prime. See, it's not so easy. And here your delta theta you evaluate at the quadrature point. Okay. And just a side remark, what happens if your delta theta is very small? The sine of magnitude of delta theta by magnitude of delta theta, of course it is defined that the limit exists, it's 1. So the whole thing, it has got a limit. If delta theta is very small, it becomes very simple. So beta becomes delta theta prime if delta theta is close to 0. Otherwise, no. Okay? Because in your Newton-Raphson, the delta need not be small, it will make a finite excursion. So delta need not be small. So the curvature update, you have to do it accurately. So this is how you do your updation. All right. So that's all how we do finite element for statics. course, we had to do it for dynamics also, but I do not think we have time to do that. So, I am just going to skip the dynamic part. That is also very, very interesting for sure, but we are not going to do that. Okay. I guess the rain did not want us to do the dynamic part.
Sign from above.
Sign from above, yeah. That this is already enough. You are torturing too much your students. Okay, so I will stop here and thank you all very much.